changing gears now in the vehicle. And I also have a PhD, but those of you who know me know that my family were hay farmers. So my PhD stands for piled higher and deeper, because I stack square bales better than I do anything on the back of a trailer or a pickup truck. So my view is a little different, and part of that is because of my background with Alabama DOT. I was with Alabama DOT, worked with Lindy here for 12 years, and then I was in private practice for a couple of years, and then now I've been at NCAP for over 16 years. And kind of like my resume at the National Center for Asphalt Technology, you know, part of our mission is to kind of operate between industry and agencies, and try to inform agencies to make good decisions on change, and at the same time we promote innovation in the industry. So that's a very exciting thing for me. And Matt, kind of an interesting story, between the time when I was with the DOT and I came to work at NCAT, I was in private practice, and I did a lot of training, and I did a training class one time up in North Alabama, you know, in the Huntsville area, and I had you know, it was a group of technicians, and I several times in my presentations I said, well, this is not rocket science, you know, and this is very basic kind of stuff. And then on one of the breaks, one of the guys took me to the side and he said, I'd appreciate it if you wouldn't say that anymore. I'm offended by that, because my wife is a rocket scientist with NASA, and he apparently had some kind of a complex about just being a technician, you know, on paving jobs. So it was kind of funny, and I was like, I didn't mean to offend you. I'm sorry about that. But it's interesting to see how it all ties together. Well, at the NCAP pavement test track, I'm sure everybody in here has most people in here know what we do, but we do research to try to improve the life cycle for performance of flexible pavement. So we build test sections on our 1.7 mile oval. Most of our customers are state DOTs, and then FHWA and private sector clients. But the objective is in 3-year research cycles to build test pavements and then compress a design lifetime of damage into about 24 months of fleet operations with 5 of these heavy triple trailer trains that you see here, so we can turn results around very quickly. Some of the things that we implement, you know, some of our findings are very short term, just right after construction. We'll help DOTs change their specifications, and sometimes it's kind of mid-term and then sometimes long term. But the important thing to point out with this is that every axle in our trains is loaded right up to the federal legal bridge limit, but not beyond. One of the things that we've learned in our research through multiple cycles on the track is that cracking performance is very much a function of the magnitude of the strain events. And one of the things that we struggle with in this type of testing, called accelerated pavement testing or accelerated performance testing, is that we can get faster numbers when we have larger strain events. A good example of that is the Texas overlay tester. Massive, large strain event. So it's a very efficient, very effective test. But the performance relationships that you get as you go higher and higher with strain events is sometimes misleading. So our axles are loaded up to that limit, but not beyond. So we do about 5 million easels a year on the track in damaging these pavements. We park the trucks once a week and do performance assessments, so we can relate the change that we've seen in our test pavements to the amount of traffic that was applied. Well, beginning in 2012, in response to the evolving research needs of our state DOT clients, we started doing pavement preservation research. Jim Mothra, I saw, was on the program, and FP2 came on board as a full funding partner with state DOTs and helped us to craft an experiment to recommend to the states that we tweaked a little bit and then built out on Lee Road 159. So beginning in 2012, for the first time, we had test sections off of the track, and it's a dead-end road, access road to a quarry and an asphalt plant, so we don't have this precisely controlled trucking. We get free trucking out there and just a precise record of what happens in terms of days, times, truck tear weights, loaded weights, axle configurations, and easels. So where we do about 5 million easels a year on the test track, we do about 125,000 plus or minus easels a year in the outbound loaded lane of Lee Road 159. And out here, you know, this is a 5.5 inch plus or minus pavement, and we've got everything from fog seals to crack seals, chip seals, microsurface cape seals, and thin overlays. And the objective is not to compare those to each other, but rather to to develop the freestanding life-extending benefit curves of each of the treatments and treatment combinations so that DOTs can then make decisions on, selection decisions on pavement preservation based on performance that's a function of pretreatment condition, and kind of keep politics out of the decision-making process and let it be a data-driven type of thing. So based on what we, the successes of 159, what we learned from 159, which we're still collecting data off of, last summer, we built more test sections off of the track out on US 280, the westbound truck lane of US 280. We're very grateful to Alabama DOT for making this lane available to us for about 4.5 miles. And we did all the same things that we did over on Lee Road 159, but then we kind of strategically expanded the experiment based on the good things that we had learned from it. And that has been incredibly useful to us, and we think we're going to yield some great results from that. Out on 280, in just that one lane that we've got our test sections, it sees over 5,500 vehicles a day. And we're still breaking that down into as precise an ESOL estimate as we can get for that lane. But there are traffic counting loops that are in the middle of these test sections that we're using for that purpose. So the two things that we want to do with this research, as I mentioned, we want to help DOTs to implement positive change. Change is a hard thing to come by in state DOTs because we have to be conservative. We don't want to make flippant changes that are gonna lead to failures. We want to make the right kind of change, but by nature we're a conservative bunch. And the other thing that we want to do is promote real innovation for the industry, and that's why I'm so excited about my job, because we get to do both of these things, and our research has implementable findings, and we get to do a lot of really creative things that sometimes bring about very, very useful change for the industry that otherwise would be hard to come by. So this is the current sponsor map for the 2015 research cycle at the NCAP pavement test track. What I've got outlined in yellow, those are our traditional states. So in addition to that being most of the SEC states, those are the states that have a climate that's pretty close to the climate that we have there in eastern Alabama, where the test track is located just off campus at Auburn University. So now what you see outside of that yellow boundary, those states have joined the project because of our partnership with a Minnesota DOT. There's an accelerated test facility up there called MnRoad, or Minnesota Road Research Project. They do the same type of research that we do, or a similar type of research that we do at the track. They've been doing it since the mid-90s, have a lot of credibility and a lot of expertise. We've always collaborated with them, but now we have an official partnership with them, and we're going to be building this summer a lot of the same treatments and test sections that we built at the track and the low ADT road and the high ADT road. We're going to do the same thing up there, so we'll be able to scope in some really harsh thermal cracking conditions and snowplow damage. So it made the project much more appealing to the northern states. Reason for that is because if you look at the territory now that we've got covered in climate extremes, it's the bulk of the country. So we're approaching half of the states that are now funding partners in our transportation pool fund, and that growth was made possible because of the partnership that we have with MnRoad. I also want to note that in addition to these states, FHWA continues to be a really important funding partner for us inside of our cooperative agreement, but also through direct track funding. And FP2 has continued the sponsorship relationship that it has as a full partner with all the state DOTs, and that has been extremely helpful to us in terms of making the right kind of selection of treatments and putting them in the right location, and then achieving the right level of construction quality in order to get results that are as meaningful as possible from the research. So in order to address my subject that I've been assigned today, I've grouped my content into these 5 categories. I want to talk about smaller, finer aggregate blends, reduced gyration level mix design. Some of these things Matt touched on. What I like to call healthy binder content that now we're trying to achieve through what we're calling balanced mix design, but that's just the way we did mix designs before the price of liquid asphalt skyrocketed, and the pendulum swung towards drier mixes. Now we're trying to get more of the right binder content instead of just a dry, cheap binder content. Reclaimed and recycled materials, and then finally, to summarize all that, what we perceive to be the need for not just a cracking test, but for possibly a suite of cracking tests that predict the distresses that, that the types of cracking that Matt talked about, but do it for the climate extremes. So our perception of that is that we have a need for simple tests, very simple tests that industry can run, both when they're doing their mix designs and when they're producing mix for the state DOTs, tests that DOTs can use to approve mix design, so not just tests that are useful for research purposes, and then tests that cover the climate extremes. So there are things that are probably going to work at the track that don't work up in Minnesota and vice versa. So what we really want to do is just let the data speak for itself and identify which tests work and which tests don't work. So on this subject of fine, small blends, we, through 5 complete cycles of testing now on the track and now 51.5 million easels, we consistently see similar rutting performance between coarse, large mixes and small, fine mixes. I think because of the success of SMAs, when we imported SMAs from Europe, when we implemented SuperPave, we thought we had to have rock-heavy mixes in order to get this larger stone-on-stone contact. But what we find is that as long as we've got a good stable aggregate structure, it doesn't make any difference what the size is or what the blend is, whether it's fine or coarse. Now, the whole trick to this is there's a longer path for crack propagation, and then also there's a higher effective binder content. It's kind of ironic to think that with the research that we've done at the track, the 2 best performing mixes are SMAs that are loaded up with rock, and then the finest blends that are loaded up with screening size materials. So you go from one extreme to the other. Well, what they both have in common is high asphalt contents. We get high asphalt contents in those rock-heavy SMA mixes by loading them up with fibers to thicken the film coatings up without having a drain down problem. And then because of coating all those screening size materials, that's what gives us high effective binder content in the finer mixes. And I mentioned this earlier this week in another presentation that I did. The 2 best mixes, arguably, that we've had on the track. The first one is an SMA that was placed in 2000 that is still in place, that's now been down for 51.5 million easels in 16 years, has no cracking in it, has no rutting in it, has no raveling. The other one is a 475 thin overlay mix. It's only 3/4 of an inch thick, that was placed in 2003. So now it's been down for 13 years, 41.5 million easels, no cracking, no rutting, no raveling. And to me, that represents, those extreme conditions that we've got to capture that, and we've got to implement that as an outcome. So we do see consistently better cracking and raveling performance. The 2 things that sold me on this, the two big things were, and I got really upset the first time we blew a tire on the track, probably back in 2001, and we had this nasty, ugly rim scar, like we have on real roads, and it gouged the pavement. And those of you who are involved with agencies knows that in a lot of cases that leads to a crack, and we have to go back and seal that crack, and it becomes a big maintenance burden. Well, I was taught when I grew up within the DOT that those fine mixes have their place on low volume roadways, but that's where we need to keep them. We need those rock heavy mixes, because I was with ALDOT when we did SuperPave implementation and started the PG binder grade system within our specification framework. Well, the first thing that changed my mind is in the first research cycle and the second research cycle, we did a lot of fine versus coarse comparisons. And what we saw was that with those rim scar damage events, after a couple of years, with the coarse mixes, and in this slide, the coarse version of a mix is on the right, and the fine version is on the left. What happens is that we'd have rim scars that would drag through a section that started a nasty, ugly longitudinal crack because of the fracture that occurs, the damage to the aggregate structure. And as soon as that rim scar hit the fine version of that exact same, all the same stockpiles, just blended on the other side of the maximum density line, all it was a scar. There was no crack. The depth of the gouge was shallower, and no crack would develop in that rim scar. That's what we've seen in that 475 mix that's now been down for 41.5 million easels. you can imagine it's got all kinds of rim scars in it, because through the years, you know, we've blown a lot of tires and we've done a lot of scarring type damage. There's no cracking has formed in that section. So that's the first big issue that sold me on this. The second big thing was an event that occurred, and some of y'all have seen this video, but we had a driver get too high in the west curve, and he dropped axles off onto a soft shoulder. We lost a trailer, and we laid down the number 2 trailer, and it just kind of drug for maybe 400 or 500 feet. Well, you might have seen the sparks that were flying up off the mat when that second trailer laid down and drug through. Well, it happened to just fall over on that 475 mix. That's where this camera is pointing in the west curve. And all it did was sort of scuff that mix up. But as soon as it hit the coarser mix that was out down past it, it just started ripping out chunks of pavement. And I mean, that is as good of a billboard that we have for durability as anything that we've seen on the track. So those really changed my mind about the potential of these finer, smaller mixes. So when we did the thin overlays as part of the preservation study on Lee Road 159, and then grew that out to US 280, the hot mix part of that is these 475 mixes. So the mixes that we used on 159, the mixes that we've used on 280 are variants of that 2003 mix. So the virgin part of that mix is 70% limestone screenings and 30% hard sand. Now that's a limestone that we wouldn't allow more than 30% of that in a surface mix in Alabama, where we're sustainable with friction at 70% because of the hard sand. So at that size aggregate blend, the hard sand is supporting the friction numbers, and we've measured years and years and years and millions of easels of safe friction. So we added recycled materials, reclaimed and recycled materials on 159, at fine fractionated wrap and shingles, and then when we went out to 280 with this mix, we added both wrap and RAS, fine fractionated wrap and shingles. But we did it kind of in an iterative way, running mix at the plant, doing some simple cracking tests back in the laboratory, trying to come to a level where we felt like we were going to get really good performance out on US 280. Interestingly, I set out wanting to do a really high age binder ratio mix out on 280 in these thin overlays. So I started out at 50% binder replacement from fine fractionated wrap and shingles, and then I bumped from 50 to 40 to 30 to 20, and then I had virgin to compare all that to, and then we did overlay tester testing, because this mix was placed on top of 100% wrap coal recycle mix, and my concern was that if we had significant deformation in the coal recycle mix, then we would have pretty high strain events potentially occurring in the thin overlays. So you know, overlay tester has massive strain events, as I mentioned earlier, but I felt like it was the proper thing to do to be conservative with these mixes. And what I found was that I didn't need to go over 20% binder replacement. So where I set out wanting 50% in order to pass the Texas DOT's criteria for overlay tester mix evaluation, I ended up with 11% fine fractionated wrap and 3% shingles. And to me, that, you know, with a surface mix, if you want to optimize durability, maybe that's a good place to be with wrap and RAS, is at those low percentages like that. You know, we think the research is, well, the data will speak for itself, but I feel pretty good about the performance that we're going to get out of those mixes. So then also on reduced gyration levels, when we first built the track, the highest gyration level in the Super Pave package was 139 gyrations. Well, when we built the first track, it was at 125, and then we dropped it to 100, and we dropped it to 80, and we dropped it to 60, and then some states now have adopted 50 gyrations. So we're working to try to get the right level of laboratory compaction in order to optimize asphalt content, and the track has been really useful to the sponsor states in order to help do that. I'm still shocked when I go do presentations in states that I don't have a research relationship with, and they're still using these massive levels of design gyrations, which give us dry mixes, and then we all get upset when we have poor durability and cracking performance in the field. Well, it's part of the reason why is design gyration levels are too high. So what we promote and what most states have kind of settled on is a kind of a locking point type of a design. At what point are you just crushing aggregate? You know, and that, I think a common place where people are saying that they're finding with their materials that they're just crushing rock and doing nothing else is somewhere between 50 and 70 gyrations. And it depends on the durability of the aggregate that you have. Any more compaction and you're not really doing anything constructive, you're doing more harm than good. And the irony is that we use higher gyration levels for higher traffic levels. So where we need more durability, we run the risk of having drier mixes. So it's really important to figure out exactly where you need to be with lab compaction to hit that locking point so you can have the healthiest possible mix out there on the roadway. More gyrations produce leaner mixes where we really need richer mixes. But lowering gyration levels alone is not enough, because if all you do is lower design gyration levels, you can if you got a good sand source, you can put more sand in the mix and get the same level of air voids, and you really hadn't necessarily done anything. So, that's not the only thing that you have to do. That's an important thing to do, but we have to remember the importance of VMA. And a lot of DOT people, they're accustomed to thinking about VMA and evaluating mixes based on VMA, but they don't really get why it's important. And it's really simple why it's important, because the VMA is equal to the air void volume and the binder, the effective binder volume. So if you're settling on 4% air voids or 3.5% air voids or whatever for your air void design, then setting a VMA level is supposed to ensure the right level of effective binder content in the mix. That's the only mechanism that we have to ensure effective binder volume. The problem with that is that VMA, where we measure air voids, VMA is not measured. VMA is calculated, and the key kind of variable in that calculation is the bulk specific gravity of the aggregates. And Matt alluded to this in his presentation. The more you add reclaimed and recycled materials to the mix, the less you have any idea what the bulk gravity of the aggregates really is. And what I have seen happen in the field, and this is something that's very near and dear to me because I get mix designs from state DOTs to build and put on the track. And in the mix design, it has the stockpiles that I have to haul down for their test sections, and it shows what their database says is the bulk gravity of those aggregates. And when we run those aggregates in our lab, we very typically get way different numbers, and those way different numbers lead to way different VMA calculations. And so, I see it out there in those data. Even though the state has a VMA that they're enforcing, they think they're enforcing, they really are not enforcing it, because the bulk gravity numbers that are being used are not right. And then that's kind of compounded by the fact that during production, it is a tool that can potentially be manipulated and abused. If you want a better VMA number on paper, you just plug in a better bulk specific gravity of the aggregate, and as long as it's not a huge difference, nobody really catches it in some cases. So we have this big need to have a better idea of what the actual bulk gravity of the aggregate is during production. And what I've kind of settled on at the track is I base all my stuff on the effective gravity of the aggregate, which you can calculate from a rice test and from an asphalt content. And even if you want to use bulk gravity of the aggregate, you can kind of develop an offset between those two, a correction factor. So at least you're calculating it, and as you run QC tests, it'll trend up and down in the direction that it needs to. So VMA then is not just sort of an abused parameter. It's a real type of a number. Now, if you start storing, if you have absorptive material and you store material in a silo overnight, then that can blow out on you. But the important thing is, if we need a better way to get bulk gravity of the aggregate, not just during mix design, but most importantly during production, because it's not the volume of effective binder in the mix design that matters. That really doesn't matter at all. What matters is what is the effective volume of the binder in production. That's what the DOT wants, is on the roadway. The mix design just says, well, it has the potential to be a good mix. It doesn't say whether it is a good mix or not. So, you know, we advocate, I personally advocate considering just a single gyration level. I mean, why do we want to dry our mix? Because we have a higher traffic level. That's where we need durability. Rutting has essentially been solved. We know how to fix rutting. We know how to evaluate for rutting in the laboratory. We know how to screen mixes that are going to have deformation problems. It's durability that's the big thing. And that's the reason why performance testing is such a big, huge deal. We have to have mixed performance testing. Matt did a really good job talking about this, but how much blending occurs between old binder and new binder? Well, that depends on whether you're running hot mix or whether you're running warm mix. You know, how much silo storage time do you have? You do extractions and recoveries and binder grading, it's gonna assume 100%, like you said. Well, with wrap, you know, the data suggests that the vast majority of wrap binder, and in some cases all of it, is available for blending and diffuses with the virgin binder. But with shingles, probably something like 3/4 of it is available for blending. So 1/4 of it is good for nothing, other than kind of giving you a false sense of what that asphalt content of that mix is. So you have to have a performance test. So I wanted to kind of talk just briefly about this deal with the finer mixes and lower mix designs, or lower design gyrations, and what we're doing for Kentucky is really a case study in trying to help a DOT to make the right kind of change. And what you see on the left is Kentucky's standard interstate mix. It's required to be on the coarse side of the maximum density line, and it's a 100 gyration mix design. So it's sort of a poster child for the DOT thinking that it's doing the right thing and getting good mixes. What you see on the right is what we have proposed in our lab design study experiment, and it's shifted towards the fine side, and it's dropped down to 65 gyration design. So we've got a finer mix, and we got a higher asphalt content. Well, the concern, of course, they have is rutting. What we need to do is, their perception is we have a longitudinal joint performance problem. Or really what they have, I think, is more of a mixed durability problem that's creating the problem with the longitudinal joint. So we want to help them solve that, but yet prove that we haven't compromised rutting performance in the wheel path. So we paved the inside lane and the outside lane of the track. That's not something that we usually do. And we lined up the longitudinal joint between the lanes right on center line, which is not something that we usually do when we're looking at mixed performance in that outside lane where the trucks run. And so far, the fine mix actually has less deformation in it than the coarse mix, and we think it's going to be a home run for them and help them change their specifications. That's going to allow them to use some of the screenings materials that are building up on them, like they are on many other state DOTs, because we want more rock in our mixes, or we think we want more rock in our mixes. So this is a close-up of how these two mixes compare. On the right is their standard coarse interstate mix, and on the left is their fine shifted mix, and these are the gradations of those two mixes. The blue is the coarse, and the red is the fine mix variant. So it's very, very close to the maximum density line, and what we find is that's a good approach to take. A benefit of this, and we've got research on the track that we're doing for FHWA in increased levels of compaction and the effect that that's going to have on performance. What I would hope is that we can also scope into that nominal maximum aggregate size of the mix, because with these 475 mixes, what we find is that they essentially approach zero permeability when the density level is in the high 80s. The mixes that are the biggest liabilities for low density are the base and the binder layer mixes, the 19 millimeter mixes, because those mixes become permeable when they go below 94%. You know, usually we think if we're at 92, 93%, well, that's a home run. We've done a great job with those mixes. Well, they're permeable. 19 millimeter mixes are permeable at 92, 93%. 475 mixes and 95 mixes and 12.5 mixes are not. So, the whole idea of density, we have to view that within the lens of how big is the mix, and that's another advantage of those finer mixes is they're impermeable at lower levels of compaction. So that kind of brings me to healthy binder content. Well, just talking about reclaimed and recycled content in the mix by total mix weight is not enough. Very typically, state DOTs will have specifications. They'll say 20% wrap RAS in the surface, 30 or 35, or in some cases 40%, wrap RAS and binder layers and base layers. Well, what matters is the binder replacement that comes from wrap and binder replacement that comes from the shingle. So age binder ratio by itself is not enough. We need to talk about wrap binder ratio and RAS binder ratio, and then even with shingles, it's better to talk about post-consumer RAS binder ratio and manufacturing waste binder ratio because of the age hardening that occurs on roofs before shingles are removed and ground up, processed for use in asphalt pavements. And this is something I'm having to train myself to do, because that thin overlay out on 280 that we built last summer, 11% fine fractionated wrap, 3% shingles. Well, if you look at binder replacement, that was about 10% from wrap and about 10% from RAS. That's what really matters. It's not the RAS percentage in the mix by mix weight, it's the binder contribution of the binder replacement that you get. We promote ground tire rubber use for sustainability. We've had really good success with ground tire rubber modification of binders, and in fact, Alabama Department of Environmental Management, thanks to Lindy, was a partner in the last track and is a partner in this track, and we're doing work specifically for them to investigate the best use of recycled ground tire rubber in pavements for mixed production and also for pavement preservation. Polymers and high polymers for cracking resistance and for fatigue cracking performance of mixes has been a big part of what we've done at the track, going all the way back to the 2009 research cycle. And we've used highly polymer modified binders in a big way that I'll mention in a little bit in the 2015 track. One of the more exciting things to me regarding recycled ground tire rubber, we've got Arizona rubber mixes, we've got SMAs and OGFCs that we've done that are just ARB binders, 12% binder replacement. But we did work this last summer with 20% binder replacement with using coarse ground rubber, -16 rubber, and we used it for plant mix production for Arizona rubber gap graded mix, but we also used it for asphalt rubber chip seals. Rod Birdsell is here, and Rod provided me with some tech support last summer, because they do some of this up in the Northeast. But what you see on the left is a coated 7 chip asphalt rubber chip seal, and what you see on the right hand side back there in the background, that's a coarse fractionated wrap asphalt rubber chip seal that we placed last summer. Now that's immediately after placement. Now this is a picture of what these look like now. So after 1.5 million easels, these look really good, and I can imagine, and Rod, you could probably talk about this some, but constituents are going to feel a little better about this than they are about just sort of the typical granite or limestone chip seal that we would use that doesn't really look like a paved surface. Well, these actually, now that we've got embedment of these particles, these coated 7s and coarse fractionated wrap, this looks like an asphalt pavement, and I could see it being something that people would be really pleased with. And the texture numbers now, we had some change in texture when we lost a few chips early, and then we had embedment of chips into the asphalt rubber binder, but the texture numbers are very, very stable with both of these sections now. You also see one of these rim scars that I'm talking about, and where it scratches the mat when we blew a tire there, and we had a driver in this section that was trying to get down to the inside lane, and it made a little scratch here, did very little damage in the coated 7 test section, but I think both of these are going to handle those types of durability issues extremely well. We also use highly polymer modified binder out on 280 in one of the microsurface sections that we placed out there. So far we've had excellent performance from all of our treatments: the fog seals, the crack seal, the microsurface chip seals, the cape seals, thin overlays, OGFCs. We got a big, and the cold recycle mix is big variety of mix out there, and excellent performance from those to date. Something really I thought would be interesting to share with this group, Florida DOT has used polymers in their binders to address their surface cracking problems. They've historically had a big problem with surface cracking of their mixes, so they use SBS modified 7622 aggressively in their surfaces, and it helped them to solve that problem. Well, when they started phasing in wrap in their mixes. They wanted to stay with their polymer binders. So they're currently capped at 20% by mix weight. They don't allow shingles, but you can put 20% wrap in your surface mixes, but you're still going to put 7622 binder in it because they want to control that cracking problem. Well, they're working with the industry in this research cycle. We've got a test section with 20% wrap and SBS 76, 25 and 30% wrap with SBS 76, and then we've also got a 30% wrap section that has a polymer modified 5828. So they're looking at the possibility of going to a softer grade of virgin binder, but still using polymers to support that higher wrap content, and then kind of let the economy of binder availability drive the mixes that contractors pick to place. Interesting thing is we've got a couple of cracks, and you see them in this picture here, in the higher binder content with the SBS 76. No cracks in the lower binder content with 76 or the higher binder content with the 5828. So we're going to be watching that and reporting on it. Now these are very low severity cracks. We paint them so that they're easy for us to document, record the X and the Y geometries, but you wouldn't see this with a network level type of a data collection vehicle. We have to do really close inspections in order to find these cracks. So performance has been very, very good so far for that. Regarding reclaimed and recycled materials, we promote the best use of every ton of wrap from the roadway. We don't need to have million-ton wrap piles that are accumulating in some of the urban markets in different parts of the United States where they're having to put beacons on top of them so planes won't fly into them. There's huge, huge resources in those wrap piles, and we need to use every ton. Now, I'm not saying we need to load up our surface mixes with wrap. I'm saying we need to use every ton as we build, maintain, and preserve our infrastructure. I think fractionation is a great way to optimize value because you end up with black rock, kind of dry black rock on the coarse side of the wrap pile, and you end up with really lean sand with a higher asphalt content on the fine side. And if I was a contractor, yeah, I would fractionate just so I can optimize the economy of the availability of those materials. The main point I try to make with people is that wrap is a moving target. With DOTs, we want to set threshold limits that we can lock into and stay on, like 20%, 30% wrap. Well, what we've seen in the track data, and that we've been doing this long enough and using state-approved wrap piles, doing recoveries and extraction grading. We started using wrap mixes in 2006, using East Alabama Paving's ALDOT certified wrap piles. And what we saw was that the recovered binder grade in the wrap at that time, because it was virgin when it was originally paved, was like in the PG 80s on the high end. Well, in 2009 and 2012, that was first generation wrap, or actually second generation wrap, because that wrap was, say, up to 15% wrap in the mix when it was originally paved. So now it's been recycled again. Well, those wrap binder grades are now in the PG 90s in 2009 and 2012. Well, now we allow more wrap in our mixes, so now we've recycled some of those, so our recovered binder grade in our wrap pile now is in the PG hundreds, in the low hundreds. So wrap binder is getting stiffer because it's multiple generations of aging, and Alabama is one of those states where we don't want to have a whole bunch of different binder grades. So we got a 76 tank and we got a 67 tank. We don't have the softer grades, so we're going back in there with 67 every time, and yet we're aging those materials more and more every time we use it. Wrap is a moving target, and I've never been an advocate of using a whole bunch of grades or rejuvenators, but we need to be as sustainable as we can be, and we're going to need to look at those technologies so that we can use every ton of wrap in the best way possible. Same thing for shingles. We've got to continue to use shingles, but with shingles and with the aging wrap, as we go through multiple generations of recycling, we're going to need softer asphalts, rejuvenators, richer mix designs, things like that, so that we can continue to push the envelope and be as sustainable as possible and be as green and as low life cycle cost as possible. It's very, very important. We need better methods to know a true production VMA, and we need to be realistic about discounting the contribution specifically of the shingle binder. And for states that are controlling quality with volumetrics, that's a challenge, because if you say, we're only going to give you credit for 75% of the shingles, but then 85% of the shingles affects the volumetrics of the mix design, it's going to make it really hard to produce the mix that the state is requesting and get a good pay factor for it. And then, of course, one of the things I'm excited about on 280 is the 100% wrap mixes under these lower ABR surface mixes that we did out on US 280. Now, these are cores that we cut from these sections after 3 or 4 months of traffic. And the cores on the left are foamed asphalt, the cores on the right are emulsified asphalt. The ones on the top were produced with a central plant, and the ones on the bottom were produced with in-place recycling. And they look the same. I mean, they really, all 4 of them, the cold recycled mix looks like hot mix. It looks like dense graded hot mix asphalt. And you can see the thin overlays on top, and the thin overlays, as I said, are 11% fine fractionated wrap, 3% shingles by total mix weight. Dry those cores out and look at them again. And even though the QC samples for foamed asphalt look way different from emulsified asphalt, after 3 or 4 months of traffic, that mix is transformed, and I really think we're going to get amazingly good performance out of all of 4 of those mixes out on US 280, and all we did was put a good thin overlay roof on the house in order to keep moisture out. And this is a plot of results from the overlay tester as a function of increasing age binder ratio, and that's actual plant produced mix. And we rush samples back to the NCAT lab and tested them in the overlay tester, and that's the reason why we locked in on 20%. I also wanted to show you this picture. This is us running our plant last summer for that mix, for the thin overlays on US 280, and we had a load cell control shingle bin, and then a conventional weighbridge control wrap bin. We're running our plant at when this picture was taken, about 165 tons an hour, and we're adding 11% fine fractionated wrap and 3% shingles. Well, look at how at this veil of material that we have coming off the belt from the wrap bin, and look at what's dribbling off of the shingle belt. That's not much material. I show this slide because all over the country people are using shingles, and they're using them with weighbridge plant controls. Weighbridge plant controls are not enough to control material that's got that kind of flow rate. You got to have something like load cells on a bin in order to even control the rate when you're feeding it at a low percentage like that. But yet, because it has 4 or 5 times the binder content of wrap, that little bit of shingles that you're dribbling into the mix can have a big effect on quality control testing in the laboratory. So kind of the bottom line to all this is we need a cracking test, and we need one bad. And we need a suite of potentially of cracking test options. My bias is that I think academia breeds divergence and chaos when it comes to this type of thing, because you can't get a PhD, and I was naive about this when I started my PhD program at NCAT. You can't get a PhD by proving something that already exists or by improving something that already exists. You typically got to make something new. Well, you make something new, and then you're going to promote it, you know. So we got all these cracking test options, and then tweaks on cracking test options, and it's chaos. I mean, we just need to figure out what works and what doesn't work. So there's promotion of many different types of tests. Well, because of my background, I get it. When Lindy's approving mix designs, it's got to be fast. It has to be able to handle a large volume of testing. But we also want to use it not just for design verification, but we want to run this test in a contractor's laboratory, you know, at least every 10,000 tons, like a TSR test. But if it's simple enough, is there something you could do within every sublot without any kind of elaborate aging that would at least give you some confidence level that we didn't change wrap source, we didn't bump the sand content up, something hokey hasn't happened at the plant that's going to blow out, or shingles running up higher than they're supposed to be running. So, you know, we've got to innovate. We've got to get to a cracking test. We've got to do it in a way that improves pavement performance. It does not have a negative impact on pavement performance. So we've got this cracking group experiment that we're executing within this research cycle. We got seven different mixes, and these are surface mixes in thin pavements. The base layer and the binder layer are highly polymer modified, so we're not going to have bottom-up fatigue cracking. But they're thin, so we've got a lot of deformation going on. What we're trying to do is crack the surface mixes, and we're focusing on surface mixes in our study because we're not building a lot of brand new pavements from the bottom up. We're doing a lot of surface work, so we need to be focused on that surface mix performance. And we've got mixes that vary from the 20% wrap control mix to 35% wrapped, and then with shingles. We've got an Arizona rubber surface mix, and we've even got the higher compaction level test section that we built for FHWA that was the scariest thing I did last summer, because I had to run it at the same asphalt content and the same temperature and use all the same compaction equipment, but yet shoot for getting 2 to 3% more density. And that scared the crap out of me, because you know, it's hard enough to get density in short production runs when you've got everything great, but to get 2 or 3% more is really, really challenging. Well, we did it. You can do it. You just got to have a lot of roller assets out there, and you got to have a good game plan to achieve that higher level of compaction. And in this study, we're looking at the test that Matt showed on his slide, and I get it. You know, we want to be mechanistically correct, but from my perspective as a DOT guy, if you could take your QC samples and throw them in an LA abrasion machine every sublot that you test and do a Cantabro test and get a good indication whether or not something's gone wrong with that mix, that's a great test to run. I mean, there's nothing mechanistic about it. It's a durability evaluation that's just nothing but a torture test. There's no, you know, other than percent loss, I mean, there's no mechanistic thing to it. But we're including that in our study because wouldn't it be great if Lindy can put that in our specifications, and it would keep somebody from running 10% shingles instead of 3% shingles like they're supposed to be running in their mix design. So we're using the Marshall press, as it's similar to how they use a simple compression test in Japan from the Japanese scan tour. There's a lot of simple things, overlay tester, but we're including a lot of simple stuff in our cracking study in addition to the mechanistic tests that we all want to see be successful, because this has got to be something we can implement for both the mix design approval and quality control testing. So to finish up with a status report, we got a high level of construction quality. We hit all of our targets last summer, which is step number one for us. We're over 1.5 million easels on the track. The only concerns we have are some transitional issues in between test sections. We've got some maintenance work we got to do because we're going from thick sections to thin sections and ramping in and ramping out. So sometimes we have some glitches there that we got to take care of. But the research in the mixes is going extremely well. We're about 500,000 easels on Lee Road 159, about 1 million vehicles on US 280 with good results. So pavement preservation across the board has been a very successful endeavor for us with the plant mix sections and the non-plant mix sections. Everything is doing extremely well, and we're very excited about generating that objective life extending benefit data for all the treatments, the non-plant mix and the plant mix. Collecting data every week in 3 locations now, not just on the track, but on 159 and on 280. And we're kind of buried in the planning process with Minroad because we're going to be building a lot this summer and working through their procurement system. We're really not as far along as we would like to be, but we'll be building sections and placing treatments this summer, and we're very excited about that. At the end of every research cycle, we host a conference. We've already scheduled the next one. It's in March of 2018. What's fun about these conferences is the focus of everything is implementation. You know, taking something with our findings and doing something with it. So that's what we do. And I'm going to go in with our mission statement. We want to help state DOTs make positive change, and we want to promote real innovation. And we take a lot of pride in doing that and kind of standing in the gap between industry and agencies so we can make sure we do the right thing. I have no perception of time, so I'm sure I ran over. I'm going through a lot of family stuff right now, and it's a little harrowing for me, but when I say I'm proud to be here, I mean I'm really, really, really proud to be here. Does anybody have any questions? That's a lot to talk about, but yes.
More binder. Okay. more binder actually makes a more durable mix.
Mm-hmm.
How does that affect the total installed cost? Do you have any idea? In other words, if we went from 5% binder to 7% binder, what would that result in the installed cost of a ton or a mile or whatever of pavement?
Well, I mean, it's all based on the economy of the liquid asphalt, the virgin liquid asphalt. That is the controlling factor in the cost of the mix designs. We're not talking about going from 5% to 7%. You know, we're talking about going, if in some of these mixes, if on the issue of gyration level designs and healthy binder contents, usually you're talking about 2 or 3 tenths more liquid. When you start talking about shifting to finer mixes, like the thin overlay mixes, and there's a big move in that direction just to keep the cost per square yard down on some of our projects, you might be talking about going from 5% to 6%, you know, liquid asphalt. So it's an economy thing that is completely driven by the cost of liquid asphalt, and it's a moving, you know, there's not one answer to that question, because is liquid asphalt $700 a ton or is liquid asphalt $350 a ton?
I totally understand, but we are dominated on durability on that 2 or 3 or 4/10%.
Right.
We're fighting over that at the expense of making a durable mix. And I can't see that cost of that raw material in relation to the installed cost, which is labor, mobilization, and all that, is really that high of a percentage.
That's the whole problem. When you look at the life cycle cost of the pavement, you are wasting money if you think because you build a cheaper job, because you're a 0.5% low on liquid asphalt on the most expensive part of the mix. If you think you've done something good by keeping the total cost of the job down, you just destroyed the life cycle cost of the pavement. I mean, it skyrocketed because you got a job that's going to fail in 7 years instead of fail in 17, 18 years. So what is the life cycle cost of that? I mean, that really is a problem, is that we're driven by initial cost of construction. Now, I was with Alabama DOT when we went from Marshall mixes to super paved mixes, and because we had these really high gyration levels and our mixes were coarse, everybody was excited, the industry and the agency, because our mixes were drier. Well, super paved says these are going to be good mixes, and they're going to be cheaper mixes because they're drier mixes. Wow, it's a win-win situation. Well, you can't compact them because they're coarse and dry, and then you're going to have really bad cracking and durability performance because they're coarse and dry. So then we've been trying to fix that ever since, you know, and I'm in complete agreement that, and the good news is that people are coming around to this. The door is open. We've been preaching about it now for a long time, and people are finally coming around to the idea that we got to have more asphalt in our mixes. Even people who got upset with me when I said, hey, the data's telling us our mixes are too coarse, too big, and too dry. People would get upset with me. Well, they're not upset with me anymore, and you hear more people in industry and more people in agencies saying, yeah, we got to do it, and it's worth it to pay a little bit more per ton for our mixes because we're going to double the life cycle performance of that mix as a result of it.
Okay, I've been at this a long time, as you know, and I never see when we present the technical, do we relate it to like an installed cost factor. And it's like, if this really, you know, to go to more binder, whatever, you have 0.5% or 0.2%, and that's a 0.5 or 1% of the total installed cost, it's really not, you know, it's a no-brainer, so to speak.
It is a no-brainer. I mean, I could work up.
And yet we don't present it that way, okay? We always leave out the cost factor or the dollar value. I'm all for a more durable mix, and you know, we put more glue in the mix, we're going to make a better road. And if it's really an incrementally small cost, and I'm not talking raw material cost here, I'm talking installed cost. Because the way I look at it, materials are probably in the neighborhood of 1/3 of the total installed cost. So again, the incremental increase is almost at a point of being insignificant.
So I think your suggestion for me is that when we, and from our team at NCAT, when we work with the state DOTs to promote this type of change, to just include numbers in our...
At least estimated
Well, and we do that. I mean, that was not within the scope of what I talked about today, but when you see my director, Randy West, when he does presentations, he very typically includes cost data in the information he presents. So point well taken.
Okay, I'm going to have to interrupt to get to the next speaker. Sorry, Ken and Buzz. We'll have to continue this conversation at break. So our next